Okay, welcome back. Let me open up my slides here just a second. Um, so today we're going to talk about, well, I'll finish talking about distributed file systems. Then we'll talk about protection and security, which of course are very important aspects of operating systems. Okay. Sharing my screen here. All right. Open up my slides. All right. Any questions at all? I hope people were successful in installing a virtual memory manager and then installing a Linux distro. Okay? I think it's very important to be able to install an operating system and to configure it and so forth. And I think by having a VM running on your machine and a Linux distribution of your choice, that's going to prove to be very useful. And I understand that many of you already have some form of Linux running on your machine. So I guess for you then, the assignment was very easy. Okay, I found that VMware was a little bit easier when it comes to installing an operating system in a virtual machine. It seems to require less upfront work. That there were some good defaults that it used, and then of course after you've installed, you can go back and change the defaults. Whereas VirtualBox, I think, required you set a lot of things ahead of time, and that made the process a little bit harder. Okay. Hopefully everybody managed to get it working. Okay. I want to talk about distributed file systems, and this is basically sort of finishing up what I started talking about networking last week. Now, of course, the file system is going to try to hide a lot of the networking details from you and attempt to present a very uniform interface. Okay, so let's take a look at this. So the whole idea behind a distributed file system is that multiple users can share files and storage resources. Obviously we have the web nowadays. A DFS has to manage a set of dispersed storage devices. So these storage devices are on the network. You have a lot of different clients and servers. Okay, you want to have the whole thing appear to an application as a nice centralized file system, no distinction between local and remote files. So that's part of the illusion that you want the distributed file system to present. Okay. Now, of course, there will be networking overhead and latency and so forth, and so applications will have to put up with those kinds of delays. Okay. All right. Well, we have the notion of a service, and that some software entity that's running on one or more machines that provide particular type of function to the clients. So clients request services or request certain functions from these service software entities. Okay, and then a server is service software running on a single machine. So you can point to a machine on the network and say, well, that's the file server, or that's the web server, or that's the database server. Okay, those are very common types of servers. Okay, And then a client, of course, is some process running that invokes a service, and these services come from a nice interface, the client interface. This is the interface that the client sees. So it's basically a list of functions that the client can call to get these services, okay? So they could be primitive file operations. If we're talking to a file server, then of course we want to create files and read and write files and so forth, okay? And, so we want the interface to be such that the client doesn't have to care whether it's talking to local files or remote files. Okay? All right, so here is a very simple picture. We have clients talking to the network, and connected to the network, of course, is the server, okay? And the clients request access to files and so forth through this interface, and then the requests are routed to the server, and the results are routed back to the client using well-known networking protocols. Okay? And one such protocol is the Network File System, NFS. Okay? I'm sure many of you have heard of NFS. It is the common networking protocol for dealing with remote files. Okay? All right, now, remember we did talk about NFS mounting before, and the whole idea of mounting is that you have your local file system, with directories and subdirectories and so forth, and you pick one of the directories to be the mount point, and you can mount another file system onto that mount point, and then this other file system becomes part of your local file system, or at least appears to be part of your local file system. You access the, you go through the mount point to access the files that are in this external file system, and it looks like the whole thing is one uniform file system. Now, NFS mounting says that this external file system can actually be coming over the network. And so you're mounting an external file system that's living on another machine on the network. And as far as your applications are concerned, those files are part of the local file system. Now, of course, when you go and open and read and write those files, the data is zipping across the network. And yes, there will be networking delays. But unless it's a program that is very timing dependent, your program doesn't have to make any distinctions between accessing local files or accessing remote files. It just goes through this very uniform file system. Okay? So that's NFS mounting, and that's one of the major developments of networking, is that you can have remote files appear to be part of your local file system. Okay. All right. So you can have this DFS model that not only manages files that are distributed across the network, but they can actually manage portions of files that are distributed across the network. And so a file may actually be broken up over different servers on the network, and through the magic of DFS, as far as your application is concerned, it's just like a local file. And not only is it coming over the network, but different portions of it are coming together from over the network. So that is quite amazing that this is happening, and you don't even have to know about it. Okay. Now, when you do have files on the network, you have a naming problem. How do you name files? And so there has to be some sort of mapping between what your application thinks it's seeing. It's opening up a file, foo.txt, okay? And that file may have come from NFS mounting, and foo.txt is out there on the network somewhere. And it may be sitting on a server that's not even running Unix or Linux, okay? And so therefore it could be some foreign file system that has a totally different way of naming files, okay? So then, of course, we have to do a naming mapping, a name mapping, so that, again, that's transparent to your applications, okay? And so there could be multiple levels of mapping. So you start out with a name, foo.txt, and that gets turned into some numerical ID, and then that in turn gets mapped to certain disk blocks, okay? And of course, those disk blocks could be on your machine. They could be who knows where on the network, okay? So again, we're hiding the fact that you're actually dealing with files on a network, okay? And you continue to use your Linux style naming conventions, and the distributed file system does all the name mapping. And so that when it finally gets to the file, the actual file on the network, it may be accessing that file using a totally different naming scheme, okay? But your application doesn't have to know that, okay? All right, so okay, I guess I've already mentioned this. You don't have to know where the file is, okay? In fact, the file may actually be replicated, through backup procedures, security, load balancing, whatever. That file may actually appear in multiple locations, and again, the distributed file system knows where to get the current copy for you. Okay, and again, that was hidden from you. Okay, you've mounted the file system using NFS mounting, and you just access the file as if it were a local file. Okay, and all this magic is happening behind your back. Okay. All right, so this is called location transparency. You're using a file name, and you may have an entire path, okay, a file path, from your root all the way down to the file name. Now, somewhere along that path was actually a mount point, and past that mount point, it was actually a mounted file system from some remote server, okay? But the file path is not going to tell you, or you shouldn't have to know that, okay, beyond this point, this path is actually from an NFS mounted file system, okay? So the name is not going to review the file's physical storage location, okay? And location independence, well, since the file path, since your application is not aware of where the file is, that means that file could actually be moved. Yeah? Maybe the network expanded and things got moved, or maybe for whatever reason, the physical location of the file may have moved, and yet your application is going to be kept unaware of that. Okay, so that's location independence. Okay. Okay, so this whole issue of file migration. Well, here if you look at some examples, Hadoop, Amazon's S3. Okay, you have no control over that. That's being managed by the server. It decides where to put the files, where to move the files, and yet because of the naming transparency, you don't have to be aware of that. Okay, you still access the file as if it were sitting right there on your local file system. Okay. All right, so there are three naming schemes. So of course the network has to keep track of where the file is, or the distributed file system has to keep track of where the file is. And so files can be named by a combination of a host name and local name. Okay, so it's, machine name colon, and then the file path from the file system on that machine. Okay, and now of course at this level we do not have location transparency or independence, right? Because we're talking at the implementation level. Okay. Number two, of course, is more at the level of your application, or at least the level of your operating system on your local machine. We do this mounting of the foreign file system, the remote file system, and then to your application, it looks like one uniform, coherent directory tree. Now, there's a feature called auto mount, okay, and that's even more amazing, is that until your program tries to open a file that is located remotely, okay, that file is not actually mounted onto your file system. So it may appear that the file is there, okay, on your local file system, but until you actually try to access that file, that's when the mounting occurs, and that's called auto mounting. Okay, so initially there's kind of a I don't know what you want to call it, a sort of a fake mounting to make it appear that this remote file system is now part of your local file system. But the actual expense of doing the mounting is put off until you actually try to access the file. Okay, that's called auto mounting. Okay, and then this third alternative is probably the least desirable one, and that's where you have some sort of global naming scheme that works across the entire network, and I guess on that will work with all different operating systems, and so I don't believe that number three is actually used anywhere. Okay, but auto mounting is something that is supported. It could be happening on your laptop and you wouldn't know about it. Okay, so the networking people have certainly put a lot of effort into not only making networking work, but making it work in such a way that your applications do not have to be concerned about it. Okay? I mean, before all this was invented, and a lot of it was invented by Sun Microsystems, by the way, and I was one of the early employees at Sun, and I saw a lot of this being developed. How do we make it easy for people to write programs that work on a network? Remember, Sun had this slogan that the network is the computer, right? Sun wanted to build servers and have servers on the network, but then that was not going to work unless they made it easy for programmers to write their programs without worrying about going out on the network. And so they came up with NFS that was developed at Sun to really try to hide the network from the developers, and they were quite successful. And you can see that now that networking is it's ubiquitous. We do not talk about single computers so much anymore, that even your laptop is connected to the network. Okay. All right. So remote file access. Okay. Well, of course, under the covers, we are sending data back and forth through the network. And okay, so you could have a dedicated server that manages the networking traffic. It could do caching. So you may have a server that's caching data that's frequently asked by the application programs, and so that could reduce networking traffic if you have a server that's close to your local machine. You know, there aren't that many networking hops, and it's doing caching. Then if you make a request for data from a file, and that file has been cached in memory, then there's a lot less networking traffic. Okay, and so and even your local machine can be caching. So the next time you try to read from a remote file, then that data is already in the cache. Okay. All right. So there, the combination of your operating system and the networking software is trying to make accessing remote files as easy and as efficient as possible. Okay. Now, in the case where a file is replicated across the network, and it could be replicated for performance reasons too. You want to have copies of the file on servers that are near the machines that applications are running. So we have to keep track of what's the master copy, make sure all the copies are synchronized. If multiple programs are writing to this file, then we better make sure that all the copies are synchronized. Okay, and remember I mentioned too that the file may actually be broken up, and different parts of the file could be in different on different servers, in different caches, and so we really have to make sure that there is a master copy that has the latest version. Okay, and so yeah, there's the cache consistency problem. If you're writing to a file and you're actually writing into the cache, well, then when does the file itself get updated? Because some other program may be reading from the file, and if the latest is in somebody's cache, then that's going to cause all kinds of problems. Okay. All right, so we have that issue. Now, there's also a virtual memory. Remember, we talked about virtual memory and how we can swap out parts of memory onto disk, so that virtual memory is going to appear to be much larger than physical memory. Well, it is possible that your swapping space is on the network. Okay, and there was a lot of work done. I guess this was quite a while ago. Well, maybe not that long ago, about having laptops with no disk. Okay, in order to keep the laptops cheap, and so that means that all the storage is on the network, including swapping. Okay, now then they that kind of design was important when disk drives were very expensive. They were spinning platters and disk arms and so forth, and so the disk drive was kind of expensive, and so to have a low-cost laptop, you would have one that did not have a disk. Okay? Now, of course, a flash memory, solid-state drives are inexpensive, and so I don't hear too much talk anymore about having laptops with no local storage. Okay? But back then, people were talking about having virtual memory where the swap space was actually on the network. Okay? So when something got paged out of physical memory, it was very expensive in terms of time, because now not only is it going out to a local swap disk, but it's actually the pages are going out over the network. Well, okay, I don't hear too much more about network virtual memory anymore. Okay. All right, well, speaking of caching then, if you're writing to a file and that file or that part of the file is in a cache, well, there is a caching update policy called write through. So as soon as you write to the cache, that data is immediately sent out to the disk. Okay, and therefore it's as if you wrote directly to the disk. Okay? You wrote to the cache, and then the caching manager immediately set that out to the disk. Okay? And so that keeps your physical files updated, so that if other processes are trying to read, then they will get the latest version. Okay. Very reliable, but of course, poor performance, because um, um, again, we're writing to the disk, which is much slower than just dealing with memory. Okay, and so reliable, but poor performance. Okay. Now, there's another way of doing it, is a delayed write. Okay, so yes, you make all your modifications to the cache. Okay, and then later on, all that writing is then moved to the disk, and so basically the cache is being flushed out to the disk. Okay, this is called write back caching. Because the data is written back to the disk. Okay, but then there is that delay. Okay. Okay. Now, write accesses are completed very quickly, because well, you're writing into memory instead of writing out to the disk. Okay. Now, there may be some savings in that. You're writing to the disk, so you're writing to the cache, and then you overwrite what you've written before. Okay, and so when the cache is finally flushed, through this delayed write, is only getting the latest updates to the file. Okay, whereas with the write through, every time you write to the cache, the data would get pushed out to the disk. Okay, and quite possibly over the network. Okay, and here, because we are delaying the writing, then if you're writing and then overwriting and whatever, then only the latest version gets flushed out to the disk. Okay. All right, so that is the delayed write. Now, of course, now you have poor reliability. Okay, you have, again, if you have other programs that are trying to read that file, well, then those programs have to be prevented from reading until the latest version of the data has been flushed out to the file. Okay, and then of course, if a machine crashes, then everything that was in the cache gets lost, and so that is an additional problem. All right, but these are the cache updating policies that need to be implemented. Okay. Now, okay, here is a variation where at regular intervals we basically flush the cache, and so we don't wait until the program closes the file before we flush the cache. Here we do it periodically. Okay, and so that it's kind of a compromise between the write through and the delayed write. Okay. Okay, this is the write on close, and this is where if a file, if an application needs to use a file for a long period of time, then and it's frequently modifying that file, then you wait until the application closes the file, which means it is done working on that file, and then you flush everything out to disk. Okay, so yes, we have the caching consistency problem. You know, if you have parts of the file cached in memory on some machine, then how can the master copy keep up with the various changes? Okay, so you know, the client can initiate a validity check. Okay, so whenever the client is going to open a file, then the whole mechanism comes into place to make sure that the master copy is updated. So all the caches get flushed and so forth. Okay, so this client initiation can happen, as I said, when you open the file. Okay, all right, I'm going to start using this file. Let's make sure this file is up to date. Okay, or before every access, like, hey, I'm about to read the file. Let's make sure the file is up to date. Okay, or at fixed intervals. Okay, and you can see that there are going to be different performance issues depending on how frequency, you know, depending on the frequency that you require to make sure that the file is up to date. Okay? Now the servers, you know, which includes the distributed file system software, it can be monitoring the files and saying, oh, look, this application is about to access this file. Let's make sure that the file is up to date, or the master copy is up to date. So here it's the server software that's making sure that the master copy of the file is up to date. So there are various ways of making sure that the cache is consistent. Okay, now if you're writing an application, you don't want to have to worry about whether a file you're about to use is up to date. And so if it's client initiated, then you want your local file server, system to make sure that the file is up to date. And then of course, if it's server initiated, then you don't have to worry about it, because the server is going to make sure that the file that you're accessing is up to date. So if you thought that the multi-process or multi-threading on your machine was complicated, now this problem is extended across the network. Okay? We have to synchronize and coordinate access to these shared resources that are on the network. Okay, any questions at all about distributed file systems? Okay, as I mentioned last week, there is an entire course you can take on networking, and you'll spend an entire semester dealing with all these issues. How do you build a network? How do the various servers communicate with each other? What's the protocol? And then you start worrying about applications. Okay, applications want to access files and other shared resources. Maybe there's a printer on the network, and then you have to deal with all of these coordination issues to make sure that the shared resources are indeed properly shared. Okay, so as I said, you can take an entire course on that, and all I can do is give you an introduction. Okay, any questions at all about this networking? Okay, all right. If there are none, then I'm going to move to another topic, which is protection. Okay, and one of the key functions of an operating system is to protect users and processes from each other, right? Yeah, we've already talked about some of these issues. If multiple processes are running on your machine, they have to make sure they don't step on each other in memory. So the operating system, basically carves out some memory and reserves it for a process to run in, and then no other process can access that memory. Now, unless, of course, ahead of time the processes agree to do shared memory. Okay. All right. So we're talking about the resources of the computer, memory, I/O, whatever, that have to be shared by multiple processes. Okay. Um, okay. So what the operating system does is, it gives each resource some sort of ID, and then it can manage these resources, through whatever mechanisms that it has to make sure that the resources are properly shared. Okay, and it makes sure that if this resource can only be used by one process at a time, such as printing or reading CD-ROM, then it makes sure that only one process can be accessing it. But then other resources can be shared, like the disk, okay, or memory. Then okay, there's a different set of mechanisms to make sure that those resources are properly shared. Okay. Now, when it comes to protection, there is this thing known as the principle of least authority, POLA. Okay, is a guiding principle of protection, and the idea is that you give programs, users, and subsystems just enough privileges to perform their tasks. Okay, and that way, if a process goes haywire, you're limiting damage because you're only giving it the least amount of authority to access the various resources. Okay, and so that is the guiding principle, that you don't give a process more authority than it needs. Okay? All right, that's also a need to know idea here. So at any time, a process should only be able to access resources that it currently requires to complete its task. No more and no less. Okay, so in my object-oriented analysis and design class, copy 135, we have a very similar principle that programs should only know what they need to know to do their task, and they should not be told anything else. Okay, that's why we have private and protected data and so forth. Okay, so similar principle here. Okay, so so how fine-grained should privileges be? Okay, so rough-grained privilege management, of course, is easier and simpler because you're doling out authority in large chunks. Yeah. For example, a typical Linux or Unix process can either be working at the user level or at the root level. Okay, it's very binary. Either you're root and you have all kinds of privileges, or your user running at the user level and you are restricted from doing certain operations that could potentially harm the system. Okay, so that's very rough-grained. Okay, either your root or your user. Okay, fine-grained, of course, is going to be more complex, but then more protective, in that you can be more specific in the types of privileges or an authority that you give to a process. Okay, and so, for example, files, right? A file can be read-only. It could be read and write, or a file can only be executed by by certain users. And so here we have much finer grained management when it comes to protection. Okay? So files come with what are known as access control lists. And so you can say that, well, this file is read-only, okay? And it can be read only by people in my group, okay? Or there could be a role-based access, okay? If you're a certain, I don't know, if you're an administrator, if you have the administrator role, then you can access certain files that people who are not administrators cannot access. Okay? So all right, so that's fine-grained protection. Okay. Now, quite often, you could have protection domains. Okay, so a domain is a set of resources, okay, resource objects, and their allowable operations. Okay, so so you can define a domain by a set of access rights, such as a certain object and a certain set of rights. So for example, you can have a file, yes, some file, and read and write access. And so you would have a set of these access rights as part of your domain. Okay? So users, processes, and even procedures within your program can be in domains. So here is a domain D1, and okay, here are 3 objects and their rights. Okay, here's domain D2 and D3, and oh look, they overlap, and so they both share object 4, which I guess could be a printer. So we have these domains, protection domains. Now, how does Unix or Linux implement domains? Okay, well, a process's domain is identified by a UID or a user ID and a GID or group ID. Okay, so that combination determines your domain. It basically says, okay, what are all the resource objects that you can access, and what can you do? What can you do with each resource? Okay, so so you may have run across your user ID or your group ID. Okay, so if you have 2 processes with the same UID, GID combination, then of course they're in the same domain, and so they have access to the same set of objects. Okay. Now, a process that has a different UID, GID combination, of course, would be in a different domain. But as you saw with this diagram, those domains could overlap. Okay, so these are all set up by the system administrator when they're system admin has commands for assigning user IDs and group IDs and saying, well, what resources are accessible within each of these domains. Okay. Now, there is a concept called domain switching. Okay, so that, for example, if your program that's running at the user level makes a system call, then there is a domain switch to the kernel's domain. Okay, and then of course when that system call is done, you're switched back to the user domain. Okay, if you have a program, okay, an executable file, and it has the set UID or the set GID bit on, then when the process is executing that program, it acquires the UID or the GID of the owner of that executable program. So you write a program, you put it out as an executable file, okay, and you set the uh, the set UID or the set GID bit on, then if somebody else runs your program, okay, they will acquire, or they will basically enter your domain, because they will acquire the UID or GID of you, the file, the owner of the executable file, okay, and then that person running the program will have a different set of access rights. Okay. Now, when that program finishes, okay, then that process will then revert back to its original UID and GID. Okay. So if you want to get if you want to have a process that's running, acquire your access rights, then you will have these 2 bits set. Okay. All right, and that kind of makes sense, because if your program needs to read and write files that are in your domain, then of course when you run that program, you want that process to then acquire those rights. Okay. All right, so that's called domain switching. Okay. Now, another way to do domain switching is that you may know about the SU command. That temporarily switches you to another user's domain. Okay, so SU is basically switching user domains. Now, quite often when we type SU, you don't give it, well, normally you would say SU and then the name of another user, and then you would temporarily be put into that other user's domain. Now, if you just type SU by itself, then by default, it's going to try to put you into the root domain. And so that's how you become root on the Linux system, is to type SU, and then of course it will ask for the root password, and even if you say SU and then the name of another user, it's going to ask for that other user's password. And if you don't know that other user's password, then of course you cannot go into that other user's domain. If you just type SU by itself, then the implication is that you're trying to go into the root domain, and then you'll have to be able to type the root password. Okay. Now, so that's domain switching accomplished via passwords. Okay. You have to know the password of the other person. There's domain switching via commands. Okay. And here that's the sudo. Okay. So if you type sudo and then the name of the command, it's going to try to execute the command with you having root privileges. Okay, so this is trying to switch you into the root domain for the duration of that command. Okay, whereas if you do SU, you basically become that user until you exit from being that user, whereas sudo says, okay, I just want to have root privileges just for this one command. Okay, so quite often if you're trying to edit a file that belongs to the operating system, okay, then you have to, you can't just type the name of the editor and then the name of the file. You have to say sudo and then the name of the editor and then the name of the file in order to be able to edit a system file. Okay, and there are other times when you have to become they have root privileges to execute certain commands. Okay, all right, so that is domain switching, using either SU sudo, or because you're allowing a program that's executing to inherit the privileges of the owner of the file. Okay, so so domain switching is something that occurs, and for most of us, we probably don't pay too much attention to it unless we have to do the sudo command. I think that's probably the most common way that we do domain switching. Okay. All right, here's an access matrix that the operating system is going to maintain this, and so here we have along the columns represent objects that, resources that the operating system is managing, and the rows represent domains. And so you can see that, okay, domain one, if you're in domain one, you can read file one, you can read file three. If you're in domain two, you can print, etc. Okay, so this is an access matrix that the operating system will be maintaining. Okay. Now, if we include domain switching, then the domains themselves are resources. And so here we can see that domain one is allowed to switch to domain two. Okay, so we can add domains to this access matrix. Okay. Now, generally, this matrix is very sparse. There's a lot of empty cells here. So most likely, the operating system is not maintaining it as a matrix, as you see here, but it has other ways of maintaining the information that you're seeing here in this matrix. Okay? It could be access control lists. So, for example, attached to file one could be a list of domains that that can read the file, or attached to domain two could be a list of resources that it can access. Okay, and so instead of having this very sparse matrix, we can have these access control lists attached to the various objects here. All right, so we have mechanism and we have policy. Now, the mechanism is something that the operating system is providing. Okay, using the equivalent of this matrix is controlling what domain has access to what resource. Okay. Now, policy, of course, is dictated by the system administrator or your company. The policy is that, okay, Ron, you're going to be in this domain, and Mary, you're going to be in this other domain. That's policy. Okay, so that's set up by the system administrator based on whatever rules the company or the school has. Okay, so there's a separation between the mechanism, which is managed by the operating system, and the policy, which is managed by the people who are running the computer center. Okay. All right, so here's our role-based access control, and users are assigned roles that grant privileges and that grant certain privileges, which then give you access to certain resources. I guess the simplest role that we have is you're a user or you're an admin. Okay, so if you create users on your computer, okay, you can give that person admin privileges. In other words, you're giving that user the role of administrator, and an administrator will be able to do things on the computer that a regular user will not be able to, such as an admin can access certain files. Okay? If you're the only user on your laptop, then you probably have admin privileges. Okay, and that is actually kind of dangerous. If you have a laptop and you're the only user and you have admin privileges, then if somebody steals your laptop or somehow accesses your laptop, then if that person impersonates you, then that person will have admin privileges. Okay, so what you might want to do is create another user on your laptop that is the account that you would normally be using that does not have admin privileges. And then there would be a separate user that has admin privileges and maybe a longer password or something to prevent somebody from getting admin privileges, whereas the normal day-to-day use of your machine will be as a user that does not have admin privileges. Okay, that's actually how I've got my laptop set up. It's too dangerous to always be admin, because if you actually accidentally do something bad, you can really clobber your system. Whereas if you did not have admin privileges, then there are more protections in place. Okay, up to you. If you do not have admin privileges, you will have to use a sudo a lot. If you do need to access some system files and you don't have admin privileges, then you have to type sudo, okay, to temporarily give you those privileges. Okay, so program level protection. So programming languages have some built-in protection mechanisms. You know, you can deal with exception handling. So that really again is up to the programmer and up to the programming shop what sort of protection mechanisms programs should have. Okay, and of course these would be very, very high level, okay, because they're at the application level. Okay. Some compilers you can ask to when a compiler generates code for your program, you can ask the compiler to put in certain checks. Make sure that you don't run off the end of an array. Have bad pointers. Those are the kinds of checks that a compiler can put in, and also the operating system will make sure that if you have a bad pointer, that you don't end up corrupting memory that's outside of your application. Certainly not corrupt memory that's down in the kernel. Okay, and so there are program level protections that are in place. Okay. All right, let's take a break, and when we come back, we'll talk about security. Okay, now protection is about making sure that users and processes don't step on each other. Security is about making sure that outsiders don't break into your system and do bad things. Okay, so we'll talk about security after the break. Okay. All right. Any questions at all about protection? Okay. So let's take a break then for 10 minutes. Come back at how about 1:10, and then we'll get into security. And I have kind of a non-technical explanation of how encryption would work, and hopefully you'll enjoy that. Is public key encryption, and it's a very common way of securing messages going back and forth, and so we'll go over that too after the break. All right, see you in 10 minutes. Okay. Okay, we're back. Okay, we're going to talk about security. Okay, come on. What's going on here? All right, security. So as I said, protection mechanisms protect against internal problems. Security measures protect against external threats. Okay, and there are various kinds of security violations. We have breach of confidentiality. Somebody's reading data they're not supposed to read. There's breach of integrity. Somebody's modifying the data that they're not supposed to modify. Breach of availability. Somebody destroys data that they're not supposed to. Okay. Theft of service. Okay. Unauthorized use of resources and denial of service. Okay. Prevention of legitimate use. Okay. So there are various ways of violating security. Okay. Check a message here. Okay. Okay. Man in the middle attack. Okay. So you can have an intruder on a network system that intercepts the data and masquerades as the sender in order to fool the receiver and vice versa. And this is how you get people's passwords or you just read data that's being sent back and forth. Okay. You know, there are a number of bad guys that do these sort of things. You know, there are the script kiddies that think it's a lot of fun to run scripts that they've gotten. You know, they're not necessarily very smart about computer systems, but they know how to run scripts, and you know, these scripts enable them to break into systems. You know, they're looking for trophies. You know, they'll grab some file and show it off to their friends, saying that, hey, you know, look what I was able to do. Okay. Now I know that from working at NASA, NASA's a big target. A lot of people are trying to break into NASA to get whatever information. And one of the protection mechanisms that NASA has are what are known as honeypots. And it's basically fake data that is kept at a site that allow these folks to go in there and think they're stealing something valuable. Okay. Now, of course, corporate thieves are smart enough to know about honeypots, and so they're after stealing really confidential data. Okay. And of course, we know all about hostile governments or even friendly governments that are trying to spy and steal whatever data. You know, corporate thieves, hostile or even friendly governments, and so the network is a very dangerous place. Okay, now it's impossible to have absolute security. I mean, if you're going to have a network, then you're going to have to deal with hostilities. It's like if you have a store. You know, if you're going to have a store, then you're going to have people in there shoplifting or robbing it. Yeah, you cannot have absolute security. Okay, all you can do is make the cost of make the cost to the perpetrator as high as possible. And so, you know, there's the threat of being caught, the threat of going to jail. You make the security hard enough for the person not to want to bother. It's like putting locks on your front door at your home. Sure, the lock is not going to be foolproof. They can kick the door in, but you're making it harder for the burglar to break into your house, and then well, maybe they'll go to your neighbor's house instead. You know, so that's basically the idea of what's enough security? And of course, security is as strong as the weakest link in the chain, right? You can put all kinds of locks in your front door, but if you leave your window open, then that's going to be your weakest chain, okay? Now, having too much security can be a problem. I can tell a little story here. A few years ago, I was in charge of putting together a lab at NASA. And so I built this wonderful lab, and then it was time to let people have log into the lab. And the security people jumped in and said, you can't do that. You can't have people logging into the lab from outside. And I said, well, that's the whole purpose of this lab, was to provide resources for NASA contractors and whatnot to be able to log in and do their testing or simulations or whatever. And so I guess my lab was extremely secure. Nobody could use it. Yeah. There was a lot of negotiations involved before we managed to allow people to log into that lab. But yeah, security's immediate response was no logins from outside. And of course, that was the whole purpose of that lab. Okay. All right. Okay. Here's a little diagram that shows different levels of security. Of course, at the physical level, you basically lock the doors. Only certain people can go into the server room. Okay, you do data encryption and so forth. At the networking level, yes, of course, we have the various protection mechanisms, and I'll talk about data encryption in just a second. How do we encrypt messages and so forth? Operating system. Okay, well, operating system can have its levels of security. Of course, we know we have user accounts with passwords and so forth that keeps out the majority of the bad characters who want to come into our system. And then, of course, at the application level, when you write your program, you make sure your program doesn't do anything bad. Okay, so yeah, the various layers of security, and on the left here, you can see that the various kinds of attacks that can be mounted against your system. Okay. All right, and then okay, here's the man or woman in the middle attack. Okay, we have a sender and a receiver, and a bad person who basically sits in the middle and intercepts the communications. And so the sender thinks it's talking to the receiver thinks it's getting things from the sender, and it's really all coming through the intruder in the middle. Okay, that's the man or woman in the middle attack. Okay, a Trojan horse attack. Okay, so a program written by one user can execute in another user's environment. Okay, and we get these sorts of things all the time. You open a bad email, and the email deposits a rogue program onto your system, and then that program can do whatever, because it's now running on your system using your access rights. Okay, and so that's called a Trojan horse attack. Okay, now you got to be careful with certain things, like if your program uses long path names, and that is seen by somebody else, that gives that person a lot of clues as to your file system, because now they see, oh, there is a path from the root down to your file, and that could give an intruder information that they normally would not get about your file hierarchies. Okay, if you have a program that uses dot, okay, now you know that when it comes to file paths, dot means the current directory. Okay, and normally you run the program and you want to access a file that's in the current directory, most likely the directory that the program's running in, then you would say, you know, dot slash and then whatever, and that says, oh, look in the current directory. Okay, well, if this program runs in another person's file system or in another person's home directory, then that program then suddenly has access to everything that's in the current directory. Okay, and so that is a serious fault in that if you write programs that use dot, okay, and then that program is run in a directory other than the one that you had originally intended, then that program suddenly will have access to will suddenly have access to that person's local directory, that current directory. So I guess if you're writing a Trojan horse, then you would write a program that has dot and then have some other person, an unwitting person, run that program, and then your program then has gained access to that person's current directory. I suppose there could be checks against that, making sure that your program never uses dot or dot dot in a file path. Okay. Okay, so we all know about spyware and pop-up, browser plugins, all kinds of ways that we can infect or be infected by Trojan horse. Okay, and quite often, well, you can see here, 80% of spam is delivered by spyware infected systems. A very common thing that bad people do is that they will infect your computer system with a program that generates or relays spam. So that's how spam messages end up being sent by many servers, because many of those servers have been infected by Trojan horse that's actually doing this in the background, and you would never know that your machine is sending out spam. Okay. Trapdoor attack. Okay, people who develop system software could put in a secret password or secret user that has all kinds of privileges, and that's a trapdoor that allows, you know, a bad person who knows about this secret password and secret user ID to then gain access to your system. Okay. A logic bomb. Okay, logic bomb. You have a disgruntled employee, and that employee puts in installs a program in the system that requires that employee to enter a password every day. And then if that employee gets fired and it's no longer around to enter that password, the program goes and does something really bad to the system, like erase all the disks or so and so forth. And so that's known as a logic bomb. Okay, and then maybe that employee knows a way of restoring the system, and so then you know there's you know, opportunity for extortion there. Okay, and of course. Okay, I was going to get to rent. I have a slide for ransomware, but we'll talk about that when we get to it. Okay. Here's a common programming error: is that your program overruns a buffer or overruns an array. Okay, and normally when that happens in your program will crash, or somehow your program will misbehave because of that. Okay, now there are ways of exploiting that, and so by overrunning an array, you could actually deposit um, data or instructions in memory beyond the array, and then those instructions can come to life and cause problems. Okay, and so that is one way to deposit bad software into a system. Okay, so okay, that's stack and buffer overflow. Okay, viruses. Okay, we all know about viruses. Yeah, it's just malicious code that is embedded in, you know, it could be embedded in a legitimate program, and so when you run that program, it deposits the virus. The viruses tend to be like viruses in nature. They can replicate. They can infect other computers. Viruses tend to be specific to a particular machine architecture, so that people who write these things are taking advantage of the low level um, low level operating system kernel system calls and so forth, and so they can really bury deep into the system and cause problems. Okay, and you know how viruses are spread. Emails that you should not have opened, whatnot. There was an incident at an army base that got infected by a virus, and what the perpetrator did was he put the virus programs on thumb drives and left them out in parking lots on the ground, and people walk by and pick up a thumb drive and then wonder, gosh, I wonder what's on this thumb drive, and they would then of course stick it into their laptop, and they got infected that way. So not that hard to get people to pick up viruses, unfortunately. Okay, and okay, there are various kinds of viruses depending on how they attack your system, and uh, um, okay, polymorphic viruses are especially nasty because there are these antivirus programs, and antivirus programs basically keep a database of code sequences that the viruses have, and so when they scan your memory and scan your disk, they're looking for these code sequences, and then they say, oh, that's a virus. Okay, but the polymorphic ones, they basically morph. They keep changing. When they replicate, they make some minor changes to their to the code, and so the antivirus software cannot keep up, and these viruses will get past the antivirus software. Okay, and the antivirus software, of course, you have to keep their databases up to date because there are always new viruses and new code sequences are constantly being put into the databases, but you have to keep them updated. Okay, okay, and then of course there are viruses that are encrypted, and then they decrypt themselves in order to execute. Okay. So there are various ways that people who write these virus programs, various ways that they can get around the security measures. Okay. All right. Okay. So categories. There are viruses that actually um, will modify parts of the protection mechanisms. Okay, so basically disabling the door locks, so to speak. Okay, there are tunneling viruses that come in through the interrupt chain that device drivers use. And so the device driver has been compromised, then during interrupts, the viruses can attack. Okay, so there are various kinds of viruses, and yeah, they're constantly inventing new kinds. Okay, here's ransomware, and that certainly has been in the news a lot. That's when a virus or any kind of malicious software encrypts important data that's sitting in a computer system, and then whoever the villain then demands payment, often in bitcoins, for the decryption key. Okay, and if you don't pay them, you've lost your data. And I've read really sad stories of hospitals and school systems, government systems, companies that have basically been held for ransom, and of course some companies will pay because it's going to cost them more to restore that data, and maybe they can't restore the data, and they're willing to pay, often millions of dollars. And if they pay in Bitcoin, that money cannot be, they can't trace it to the recipient. Okay? Another thing that the villains can do is threaten to post the data. Hey, I've gotten all of your customers' phone numbers and social security numbers and bank account numbers, and if you don't pay up, I'm going to post all that data onto the web. And often they will post, a small part of the data just to prove that they actually or to convince the people that they actually have all of the data. Okay, so that's ransomware, and I seem to be reading more and more news stories about that. Okay, keylogger virus. This is pretty nasty. Basically, this virus is recording everything you type, and then periodically sending all of that to to the villain, and they can see, looks like you were logging into a bank, and gosh, you just typed in your username and your keyword and your password, and all of that got logged by the virus, and that now the bad guys have your bank account. Okay, so that's a keylogger virus. Okay? Port scanning. Now, from our discussion about socket programming, you know that every operating system has a number of these software ports, and each port has a number. I think I mentioned that port numbers below 1024 were reserved, and then any port number higher than that you can use for whatever. And I think in my examples, I use port 5000 as a way of having to make a socket connection. Okay, well, port scanning is software that basically scans the ports of your operating system, looking for a port that wasn't properly closed or wasn't properly protected, and then it's going to make a connection to that port. And so now the perpetrator has a communications connection to your operating system, and who knows what they can do with that. Okay, denial of service. Okay, let's say you have a corner grocery store, and for some reason you got some organization mad at you, and so what they do is they get a bunch of people to stand around in front of your store, and that keeps your customers from going into your store. Okay, I mean, it's perfectly legal to stand on the sidewalk, but they're going to do it in front of your store and prevent customers from going in. Okay, same sort of thing happens with denial of service. Okay, you have a server that's responding to clients, and so they flood that server with requests. Okay, and many of you know there's a utility program called ping. You type ping and the name of a server, could be a URL or IP address, and ping basically sends a short message to the server, and the server is supposed to send a short message back. Yeah, basically this is a test of whether or not a server is alive. Okay, and the ping can automatically repeat. So every second it sends a ping and then expects a response back. Okay, well, if thousands and thousands of users ping your server, then your server is tied up responding to these pings, and it doesn't have enough bandwidth to respond to other client requests. And so then that server can no longer provide services because it's tied up with all these bogus requests. And so that's called denial of service, because you're denying legitimate clients from getting service. Okay? And these attacks happen every once in a while, and network management software can often tell that this is happening. They can detect this sort of thing because there are all these requests suddenly coming in, and they can do things like shut down a link or whatever to prevent this kind of attack from continuing. Okay, now but then you have to be able to distinguish a denial of service attack from a website that suddenly became very popular for some reason. You know, maybe it's some kind of streaming service, and whatever they're streaming has become super popular, so everybody is trying to access that server. Now, is that a denial of service attack, or is it just a website becoming very popular? Okay, that there have been stories of students writing bad fork code. You know, on the midterm, there was that one program that did a bunch of forks, and then each fork child process did some forks, and so you can imagine that the number of processes can grow exponentially when you have this sort of program. And you know, if the forks are in some sort of infinite loop, pretty soon you can flood the network with you know, if each of the processes are doing something on the network, pretty soon you can flood the network. Okay, and so that would be an unintentional denial of service. Okay? All right, well, how do we design a system for security? Okay, well, one way is to make the system design public. Okay, that way everybody can see how the system was designed, and so if something goes wrong, it would be noticed by a lot of people. Okay, the default should be no access. That reminds me of my experience building that lab at NASA, and the security people said, "Oh, we won't allow anybody access to it." Well, yeah, sure, that would make things very secure, but the principle is that you allow access only to the people who need access, and then for everybody else, the answer should be no, you cannot have access. Okay, always check to make sure that people who are using your system have the correct authority, that they have their access rights are set up properly. Okay, and again, each process should be given the least authority possible. Just give each process what they need in order to do the job. Okay. You know, if the protection mechanism or the security mechanism is itself very complicated, then it makes it actually easier for people to find ways of getting past it, right? If it's a very simple mechanism, um, it may be a very simple and effective mechanism, and it's harder for hackers to get around that, okay? Um, Make it, okay, it says here, psychologically acceptable. You know, if the security is so onerous that, you know, it gets in the way of people doing their job, people are going to try to find ways around it. And that's not good. Okay, so you want the security to be reasonable and for people to understand, okay, why that security is there, so they won't try to get around it. All right. Obviously, passwords is one security mechanism. Problem is that people pick bad passwords. Okay, there was a study done, and they found out that, okay, what are the most likely passwords that people will have, and here we have it. And it turns out that when they ask people to look at this list and to say whether or not the password they're using is on the list, 86% of the passwords that people were using was on this list. Okay, so that makes it easier for people to guess passwords. Now, of course, I still see systems that ask when they say, okay, choose your password, and they say, well, it has to have capital letter and number, has to have a some special symbol and so forth. Well, that makes it harder for a person to guess the password. However, the hackers that are trying to break into your system, they're not sitting there typing in passwords all day, trying to guess. What they have is a program that randomly generates passwords, and of course those programs, it doesn't matter what the character is because it's going to randomly go through all the characters, and so having a password with upper and lower case and digits and special symbols is not going to make it any harder for a program to manage to guess your password. Okay? But apparently it's still possible to guess people's passwords. I mean, try their first and last names and see what happens. Okay. All right. And then if you have a program that requires a password, let's say you're writing some web application and you're asking for username and password. Okay. Now, what you do not want to do is if the user types in a wrong password, you do not want to immediately respond and say, oh, your password is wrong. Okay. Because if you respond immediately, that means that a password guessing program will be able to try many passwords in a short amount of time. Okay, you should always put in a delay, even if it's half a second. Okay, whether the user typed in the correct password or the wrong password. Okay, you do not immediately log the person in. You do not immediately put out an error a warning message saying that the password is wrong. You wait half a second, okay? That forces the password guessing programs, then the password guessing programs have to wait for your response. And if you put in 1 or even half a second delay, that means that these programs cannot churn through hundreds and hundreds of guesses in a short period of time. Okay, so that is a mistake that a lot of these programs that require a login have made, in that they respond immediately. All right, of course there are firewalls, and so here we have a company's computers. Okay, you do not have the company's computers connect directly to the internet, you go through an intermediate server called a firewall, and DMZ actually stands for demilitarized zone. It comes from warfare, and the company's computers actually go through the DMZ, which then does a lot of security checking and so forth and so on. And um, requests coming from the internet will be blocked by the firewall. So a request comes in, goes into the DMZ. The DMZ says, no way that you're allowed to come into our computer system. And so this intermediate firewall here then is going to keep bad requests from going out and bad requests from coming in, okay? Firewalls have all kinds of configuration settings. And so in the firewall, you can say, okay, I know that requests coming in from a certain server, I know those requests are okay. And so you can say in the firewall, always let requests from a certain server to come in. You can configure in the firewall that, oh, we've gotten a lot of hackers coming from country XYZ. And so you can say that, well, any IP addresses coming from that country are going to be blocked. Okay, so there are things you can set with a firewall. Okay. All right. Any questions so far? Okay. Now, I'm going to give you my non-technical security lecture, and I hope you don't mind the cute cartoons, because I actually gave this talk, gosh, it's been almost 6 years ago, to high school teachers who wanted to learn a little bit more about computers. And so I was one of the lecturers that I talked about sorting and searching and various other topics in a very non-technical manner. And this was one of my topics, was how to protect messages going back and forth on a network. So I will give you this non-technical lecture. Okay. All right. So here we have Jill. Jill is sending confidential data to John. Okay. They plan to make 7 million widgets next quarter, and they don't want their competitors to find out. And so the number 7 is confidential. Okay. But if you're going to send email, okay, it's like sending a postcard. Okay. Anybody can read the message. Okay. So you don't want to do it that way, right? All right. So how can we protect messages going from Jill to John without Bart, the evil hacker or corporate spy, from intercepting that message? Okay. All right. So that's the goal of the next a few minutes. Okay. All right. Well, Jill wants to send confidential data, the number 7. Okay. And they can have a shared secret. Okay, so let's say that Jill and John share the secret number 12. Okay, and so what Jill's going to do is Jill's going to encrypt the data by adding 12 to the number 7. And so Jill is actually sending 19. Okay, and then John will decrypt the data by subtracting 12, and then John gets the confidential number 7. Okay, so Bart here will not be able to decrypt because Bart doesn't know the shared secret 12. Okay. All right. So Bart cannot get the number 7 out of the message. Okay. All right. So this will work as long as Jill and John have a shared secret. Okay. And well, that presents some problems. Okay. Jill and John have to arrange beforehand to share the secret 12. And what if Jill doesn't already know John? So they cannot agree to share the secret 12. Okay, so having a shared secret only works under limited conditions. Okay. All right, and then what if Jill wants to send the same confidential data to all her vice presidents at the same time? Okay, so do they all have to share the same secret? Okay, so all right, how can Jill and her recipients share a secret then? Okay, because we do need a shared secret in order to get this encryption to work. Okay. All right. Well, okay. So what I'm going to describe is public key cryptography. Okay, which uses a shared secret, and I'm going to show you how this will work. Okay, but I'm going to simplify it quite a bit. Okay, so now let's pretend, in order for me to show you how public key cryptography works, let's pretend that multiplication is a one-way operation. In other words, if I multiply two numbers together, like 4 and 5 to get 20, I cannot recover the original numbers, right? So you know, if I have 20, I cannot recover the 4 and the 5. Okay, so I can't do a division to recover the original factors. Okay, so we're pretending that multiplication is one way only. Okay. All right. So how can we do public key cryptography then? Okay. So Jill chooses a private key. And this is private to Jill, so she can choose whatever number she wants. So let's say that Jill has chosen 10. Okay. Now, John, who's going to be receiving messages from Jill, he chooses a private key. Okay. And that's a number only known by John. And let's say he chooses 8. Okay. So Jill has a private key 10, known only to Jill. And John has a private key 8, known only to John. Okay. All right. Well, let's see how this will work. Okay. Now, Jill announces a public key. Okay. And let's say it's 5. Okay. So it's public, so everybody can see the 5. Okay. That's not a secret. Okay. Now, Bart here, Bart can see the public key. All right. But Bart cannot see the 2 private keys. Okay. All right. Now, Jill creates her public private key. Okay. And she does it by multiplying her private key by the public key, and we get 50. Okay. Now remember, multiplication is one way. So we cannot recover the 10 from the public private key. Okay. Now, John creates his public private key by multiplying his private key by the public key. And so his public private key is 40. Okay. Now, again, because we're pretending that multiplication is one way, knowing the 50 and the 40 is not, okay, we know the 50, we know the 40, and we know the 5, but we still cannot recover the 10 and the 8, right? Because multiplication is one way in our pretense here, okay? All right, okay. Now, what's the goal of all this, okay? Remember, we're still trying to create a shared secret between Jill and John, okay? So Jill multiplies John's public private key by her private key. So Jill is going to say 10 times 40 and get 400, okay? John is going to multiply Jill's public private key by his private key, and 8 times 50 is 400. Now they have a shared secret. Okay, so now they both have a shared secret of 400. Okay, right now, again, because each person had chosen a private key that nobody else knows, And by all these multiplications, we got the two shared keys, the two shared secrets, and we cannot recover, okay, because the private keys are not recoverable by outsiders, then the shared secret is really secret between Jill and John, okay? All right, so now Jill can encrypt the number 7 by adding the shared secret, okay? And John can decrypt the confidential 7 by subtracting the shared secret, okay? And so here, the 407 is sent across, and Bart cannot decrypt because there's no way for Bart to know the shared secret, okay? So you can see here that Jill and John did not have to agree ahead of time that the shared secret is 400. They both calculated the shared secret based on the public key, okay, that Jill had announced, the 5, and then John and Jill each had picked a private key. And so through the various multiplications that you saw, they managed to calculate the shared secret, okay? Right. So now, what happens if there are multiple recipients? Okay, so now here's Mark, who is John's twin brother, and Jill wants to send the confidential message to both Mark and John. Okay, now you see that each person has chosen a private key. Now Mark here chose 2, let's say. Okay, all right, and Jill needs to send the information out to everybody. Everybody's picked a private key. Yes, great. Jill announces the public key, 5. Okay, and so now each person generates a public-private key. Okay, so here Mark is now 2 times 5, so there's 10. And of course, we already saw that the 50 and 40 that John had. Okay, and now Jill, okay, is going to have a shared secret with each of the recipients. Now we already saw that Jill had a shared secret of 400 with John, and now by the multiplications, then Jill will have a shared secret with Mark of 100. Okay, so Jill takes Mark's public-private key and multiplies it by her private key. So here's 10 times 10, which gives 100. And then Mark takes Jill's public-private key, which is 50, multiplies it by his private key, which is 2, and gets 100. And so now between Jill and Mark, they have a shared secret. Okay, so Jill has a shared secret of 400 with John, and Jill has a shared secret of 100 with Mark. Okay. All right, so then we can send encrypted messages. Okay. And poor Bart cannot decrypt any of those messages, okay, because Bart does not know the shared secrets. Okay, all right, this is how it works. Now, of course, in real world, we don't do simple operations like multiplication and addition, because obviously multiplication and addition are not one-way operations, but we can find one-way operations that will allow us to compute a shared secret. And that shared secrets start out with private keys that are known only by each person. Okay, there's a public key that's going to be used by all the people who are going to be, the group of people who want to send and receive messages. They will have a public key. Somebody publishes it. Using the public key, and their private keys, they generate their public-private keys, okay? And then by multiplying the public-private keys by the private keys, we generate the shared secrets, okay? Now, in real life, the same thing will happen. There will be a set of private keys, there'll be a public key, except that the operations will not be simple multiplications and additions and subtractions, okay? In real life, we use prime numbers and modulo arithmetic. If you pick two very large prime numbers and multiply them together and get, an even bigger number, it's very hard to factor that big product into the original prime numbers, okay? Because there are so many prime numbers that if you pick two of them and multiply them together, from the product, it's not easy to determine what the original two prime numbers were, okay? So they use big prime numbers and modulo arithmetic, okay? And that, we would say, will be the one-way operations that in real life this cryptography will use. Okay. Now there has been a lot of concern that with quantum computers, okay, that are just blazingly fast because they can do so many things in parallel at very low levels, that just through guessing that they would be able to break these encryption schemes. Okay, so that is a concern. But once again, if we make our keys long enough, then it'll be harder for computers by mere guessing to be able to decrypt the messages. Okay. All right. So when you are talking to a website, okay, and you're using secure HTTP, well, your browser and the server did this little dance that I just showed you. There's a public key that's been published somewhere, and then your browser chooses some sort of private key, and the server has a private key, and then a shared secret is established between your browser and the web server, and we can have encrypted communication. Okay. Now this sort of cryptography is called a Diffie-Hellman. Okay, it was published by these two gentlemen in 1976. So they get all the credit for it. But it turns out that it was actually invented 6 years earlier by the British government, but they classified it because they were using it for their encrypted communications. So, well, they didn't get the credit for it. So these two guys got the credit for it, okay? And so, as I said, if you're visiting a website that is HTTPS instead of just plain HTTP, then this little handshaking took place to establish the shared secret between your browser and the web server, and then we can encrypt the messages. Okay. All right, so this was my non-technical explanation of how this is called public key encryption, because, as I said, there's a public key that is published. Okay. Any questions about it? Okay. I hope you get the idea of the basic mechanism that enables this all to work, and of course in real life, the one-way operations are a lot more complicated than just simple multiplications and additions and subtractions. Okay. All right. Any questions about this? Okay. As I said, I gave this talk 6 years ago as a part of basically a weekend class that the computer science department put on for local high school teachers who wanted to learn more about computers. And so I kind of kept it at a fairly a simple level. Okay. There are entire semester courses on cryptography. I know that the computer science department has a course on computer security. I didn't check computer engineering's a list of courses, but I'm sure there's a course on computer security. Okay. All right, I just want to point out to finish that computer security is a hot field. You know, along with data science, data science has become a hot field because of all the data that needs to be analyzed. Well, that data is being zipped around on the network, and data has to be kept secure. And so if you want a very good career, yeah, you can go into computer security, and then you can operate in this dark, shadowy world. Okay. All right, I got to tell you an anecdote. Okay, now, SRI, which stands for Stanford Research Institute, although now it's actually independent of Stanford, but it's one of these research institutes. I think they're located in Menlo Park. But I had an opportunity. Let's see, was it when I was working at NASA, or was it when I was working at IBM? I think when I was working at NASA, we had an occasion to do a project with SRI. Actually, I'm thinking maybe this was something with the computer science department. But anyway, we were working with SRI. We were working with their security people, and so it's going to be some joint effort. And I mentioned earlier that hackers like to break into systems and steal something as a trophy. Okay, and the SRI people are kind of like that too. The security people, they like to brag about their little triumphs. Okay, so they told me a story. Okay, they were working on a project, and they noticed there was an intruder from the outside trying to break into their computer system. Okay, and you would think, of course, the SRI, the security people, or the people working in security would be able to detect this sort of thing, and sure enough, they did. So they detected an intruder. Okay? Now, being security people, they figured out the route that this person was taking through their network to get into their try to break into their system. So they traced the route back and broke into the intruder's computer system. Okay, and they went in there, and it was a person, and they said, well, we have to have a trophy so that we can let that person know that we had broken into his system. Okay, so they rummaged around through the intruder's file system and found the person's resume, and so they extracted the resume, and it turned out the intruder was actually a woman who has a PhD in computer science, and she has been caught before breaking into computer systems. And so what they did was they sent her an email message with the resume saying that, look, we know you were trying to break into our system. We traced it back and we broke into your system, and here's what we stole from your computer. And it was her resume. And needless to say, they never saw her again trying to break into their computer system, or at least they never detected her trying to break into their computer system. Okay, and so they were all kind of bragging about this, And then they finally admitted that, you know, she's the type of person we would like to hire into our group. But of course, you know, she had been convicted before, having been caught, and so there's no way that SRI would be able to hire her. But you know, that's the kind of people who work in security. You know, it is a dark, shadowy world, and if that turns you on, then computer security is the career that you should look into. Okay? All right. That's all I have to say about protection and security. And if you, as I said, if you want to learn more, then definitely you should take a course in it. Okay. Any questions? Okay. All right. So next week is actually our last week. And what I want to do is go over some case studies. I think in the past, when I've taught this class, the case studies were Linux and Windows, which, you know, are extremely popular systems. It wouldn't hurt to know a little bit about how they're implemented. Now, when it comes to Linux, you saw a lot of Linux at the top level, right? You saw all these POSIX calls that I had you use, and so you were dealing with processes and files and inter-process communication and so forth. But we can look at a bit about how Linux actually implements all that. Okay, so that could be one case study. Another case study, as I said, with Windows. So we can look at Windows 10. And see maybe how it differs from Linux and how Windows implements, you know, processes. And I mean, Windows will do everything that Linux does, okay, but in a different way. Okay. Another possibility would be the Android operating system, because you know, that's everywhere. You know, most iPhone, most mobile phones use the Android operating system. Of course, Apple uses their own operating system, but there are a lot more Android phones out there than there are iPhones. So that could be another operating system that we can look closely at. So I think we'll have time for 2 or 3 close looks at operating systems. So you know, I'll decide, or if you have a favorite, just, yes, send me a note or something, or put it in a discussion forum, and then we can spend next week doing these case studies. I'll also talk a little bit about the final exam. I suspect they'll be very similar to the midterm in terms of format. We had some multiple choice questions, and let's see, did the generally when I do an online exam, it's multiple choice questions plus problems, but I don't remember. Okay, see, I've already forgotten the exam that I gave for this class. Was it only problems, or was it a combination of multiple choice and okay, take a quick look. This is midterm preview. Oh, it looks like it was only problems. Okay, well, I haven't put together the final exam yet, so either it will be a combination of multiple choice questions plus a few problems, or it could be problems only. Okay, but it will cover the entire semester with emphasis on the second half. Okay, so we'll talk about excuse me, we'll talk more about that next week. Okay. All right, any questions? Okay. I believe I'm supposed to remind you that you should be filling out those course surveys, the SOTs. So please do that. And then I did post an announcement that there are more internships at NASA Ames. So take a look at my NASA. Oh, here it is. My NASA webpage, and okay, we have 1, 2, 3, 4 internships that are open for resumes. Um, um, a couple of them have been filled. Um, and they go fast. So if you're at all interested in these internships, you should send me your resumes as quickly as possible. Okay. There was a chat question asking me, am I teaching 152 next semester? Well, the answer is no, because I'm going to take a break from teaching. I've been teaching 5 classes, sometimes 4, each semester for the past 7 years, and I really need a break. So I'm not going to be teaching at all next semester. Okay, and then after a break, I may come back, but who knows? I expect to be going back to NASA Ames. I was a senior scientist there when I decided to leave and go into full-time teaching. But I'm going to take a break, and because I have this grant, at the very least, I could be spending time working on this grant and working with the interns that we hire. And so I'll be back at Ames again as a senior scientist. But at the moment, Ames is locked down because of the pandemic. And so who knows when it will open up again. So anyway, that's a long-winded answer, but the answer is no. I will not be teaching any classes at all next semester. Okay. Any other questions? All right, then I will sign off, and thank you for coming, and have a great weekend. Okay. All right, where is the sign off button? I've got so many things on my screen now. Oh, there it is. All right, stopping sharing and ending. Bye.